Hi, this video will cover one of the most important experiments in this section of learning. It's named after the two main experimenters. The Rutherford-Marsden experiment changed entirely the world's understanding of the atom. It was, you might call, a paradigm shift. This is often used for an extended answer question in your IGCSE physics exam. These are worth 6 marks. Now that's 7% of one paper, or 10% of a C grade. So that 10% of a C grade could mean the difference between you getting the C grade or ending up with a very low D. You have a question that you'll need to answer. Let's start by watching this short clip.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounced off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of 2 kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
So let's see if you've got the main points of the experiment. Thomson suggested that the atom was like a Christmas pudding, or as he called it, a plum pudding. Now the plum pudding, or the Christmas pudding, is made up of cakey, doughy mixture, and embedded inside are currants or raisins. You might think about it a bit like maybe a chocolate muffin or something like that. Inside the dough of the chocolate dough, you've got your chocolate chips inside. Essentially, his idea was that the raisins represented the negative charge. So they were small and they were condensed. It suggested that the dough, or in his model, that sticky stuff that holds it all together, was the positive charge. And this was the idea of the atom that many people had for a long time. And It worked for most ideas. It was kind of a solid lump, much like we talk about when you talk about in year 7 or year 8, you talk about particles and things like that. Essentially that's what's going on. So the idea was that this solid lump of positive charge, all spread out fairly evenly, held in the negative charge. And this model worked very well, until along came Rutherford and Marsden, and they decided to try an experiment. This experiment here takes a little bit of explaining. So they set up their experiment here firing alpha particles. Now the source here was firing these alpha particles at what's referred to as gold foil. Well, imagine your foil in your kitchen, exactly the same thing, except this was gold. In fact, this is so thin that it's actually around about 2 atoms thick. That is extremely thin. Now gold's quite special because it actually holds itself together. If you were to try and do this with most materials, they would start to disintegrate when they got down to just 2 atoms thick. Now, as you might expect, these alpha particles were fired at the gold foil and most of them came out the other side. Just going to show you what we might expect. So, on the left hand side here, this was the Thomson model, the plum pudding model. So we had the soft squidgy positive charge holding in the concentrated electrons in there, or the negative charge. And in that case you might imagine if you fired these hard alpha particles at this plum pudding, a bit like firing bullets at a Christmas pudding or bullets at a chocolate muffin, you pretty much expect them to come out the other side. And that's exactly what they started to see. When they moved the detector around the back of the gold foil, they found lots and lots and lots of the alpha particles colliding at the back there, and they made tiny little flashes of light. The problem was, that's not the only thing that happened. I'm just going to go back to the first diagram. So what happened then, quite surprisingly, is that some of them went off at random directions. Now, if we imagine firing a bullet at a very thin piece of paper, you'd be very surprised if suddenly the bullet went firing off at strange angles. In fact, you'd be extremely surprised if the bullet came firing back at you. How is this possible? Well, as suggested in the video, it took a very long time to come up with a model. But Rutherford and Marsden did manage to come up with a model. And this model took some time to understand. And perhaps if I take a moment to try and explain you through the model, it might help as well. So Rutherford and Marsden suggested that actually, since most of the alpha particles did go straight through the gold foil without any real change in direction, that actually most of the atom must be empty space. Now, this is a little bit similar, isn't it, to the model you've been taught in chemistry, where you've got the nucleus and you've got some electrons located around the nucleus. And in fact, in that case, the alpha particles can just pass straight through most of the time. They don't go anywhere near the nucleus, and they just pass straight through, and our alpha particles are detected on the other side. So that was their first assumption. Number one, they thought that most alpha particles go through, so most of the space must be empty. That's the first point. The second point they came up with was that because the positively charged alpha particles, some of them were bounced back. Here you can see they're repelled back. This is an alpha particle, or here we've got another alpha particle being repelled, and another one. Because some were bounced back, they must have been repelled by a positive part of the atom. Here I've labelled in the middle there as positive. So that's the second point, guys. Some of the positively charged particles were scattered back. These must have been repelled by the positive part of the atom. This part I've located here. And the third part, and this is really quite difficult for some people, but the third part is this. Because the alpha particles were moving so fast, in order to turn this round, stop it, and turn it round all the way back where it came from, they must have had a really, really dense, hard, solid area with all of the positively charged particles compressed into a small space. So the positive nucleus here must have a very large mass compared to the alpha particle. Think of it like this. If a bullet was fired at something and it bounced back, you'd expect the thing it was fired at to be quite hard and quite dense. If, I don't know, you held a piece of paper here, you wouldn't expect the bullet to be reflected. If maybe you held a brick or lots and lots and lots of bricks, you might possibly expect that the bullet might bounce back. And again, very dense, very hard. So we've got three things there that this experiment suggests, and I'm just going to run through these slowly. So, to summarise, there are three main things we need to pick from this question. Rutherford and Marsden noticed that most of the alpha particles went straight through the foil, and therefore most of the atom must have been empty space. If you recall, this is the results they were seeing there. Most of them went straight through, so therefore most of the atom must have been empty space. The second conclusion: since some of the positively charged alpha particles were scattered backwards, then they must have been repelled by a positive part of the atom. Remember, positive repels positive. Again, let's have a quick look at this. So they suggested that the positive region must have been what was responsible for repelling the alpha particle. And the final conclusion that we can take from this experiment is this last one here. Because the alpha particles were moving very, very fast, they must have had a very large momentum. Now, you won't have covered momentum yet, but that's to do with mass and velocity. So the bigger something is, the heavier something is, the faster something is moving, the more momentum it has. Think of a truck has a lot more momentum than maybe a bicycle does. The positive nucleus of a gold atom must have had a large mass in order to stop some of the alpha particles from moving forward and then repel them back. So if we take a look here, remember some of these were stopped and sent backwards, stopped, sent backwards. So there must have been very, very concentrated mass, large mass, positively charged, and most of the atom must have been empty space. And that's what we're going to explore in the next lesson.